Thank you, everyone, and thank you so much for organizing this conference. I've learned so much from yesterday's sessions, and I'm excited for the discussions to continue today. This is joint work with York Dreschler, Ira Globus-Harris, Audrey McMillan, and Adam Smith. So in this work, I'll begin by describing why we look at confidence intervals for the median, why this is why this is an interesting problem, both practically and technically. And then I'll talk about some algorithmic approaches. And I hope that by the end, we'll come to some insights for noisy measurements beyond just medians. Okay, so in this work, we focus on one of the key measures of location, which is the median. And we look at the median for two reasons. One reason is that on the practical side, it's a common and fundamental statistic, especially for skewed distributions, estimating the incomes. And it's also been shown that there's a really interesting connection between robustness and differential privacy. So starting from Dorkley in 2009, robust algorithms seem to offer better utility for differential privacy. And in recent work, we also showed that for simple linear regression, this algorithm called DPTL-Sen performs really well for small data set regimes. And this algorithm relies on a differentially private median. So that was kind of one of the motivations for looking at confidence intervals for the median. On the technical side, medians are an interesting challenge for differential privacy because the accuracy of the median is so data dependent. It depends on the exact data distribution and reveals more than just the median. And existing DP algorithms for the median may not naturally extend to confidence intervals. So first, considering the non-private, non-parametric confidence interval for the median, if we have a data set X from sampled IID from a distribution, then the rank of the population median in the data set is distributed as a binomial with parameter 1/2. So we know that the rank of the median falls into this interval of percentiles with probability 1 minus alpha. So using those percentiles, we can output the confidence interval as the values that correspond to those percentiles in the data set. Now when we consider this problem under privacy, it's even more important to consider non-parametric confidence intervals. And one of the main reasons for this is that we want to avoid making distributional assumptions as much as possible because getting these correct is more challenging under privacy. We have to spend privacy budget to explore the data and to confirm our assumptions. We also cannot simply return the noisy estimates of the endpoints of the non-private interval, XL and XU, because when we're adding noise to those estimates, we might get some confidence interval that's smaller than the non-private interval, and therefore will not have adequate coverage. And in particular, we want to, as we've talked about a lot today, we want to consider these two sources of error. So the error due to sampling and then the error due to privacy noise. And we look at two approaches to providing confidence intervals that take both sources of error into account. So one approach is the union-bound approach, where we account for both sources of error separately. So for example, to get a 95% private confidence interval, we want to compute the 96% non-private interval, which considers the sampling error, and then compute another confidence interval that captures the non-private interval with 99% chance. So here we're accounting for the two sources of error separately and bounding the failure probability of both using a union bound. The problem with this is that it results in overly conservative confidence intervals, both in terms of empirical coverage and in terms of the width of the interval. So a better approach, if we can do it, is to exploit the relationship between the two sources of error, and this will provide tighter confidence intervals. But in our experience, this seems to require sort of tailored coverage analysis And one open question is whether we can make this a more general process. In this work, we tested out a bunch of algorithms empirically, and I want to focus on two of them and sort of giving these two different approaches. So one is to apply post-processing to a noisy estimate of the CDF. And this provides decently tight confidence intervals. And you can also release the CDF estimate on its own because the median confidence interval is just a post-processing. So this provides a lot of utility beyond just the median. The other approach is to directly estimate the endpoints of the confidence interval using something like the exponential mechanism. And this provides tighter confidence intervals, and also because we have some error guarantees on the exponential mechanism, we can get bounds on the size of the confidence interval with respect to the distribution of the data. And for the sake of time, I'm not going to go through the related work, but there's a lot of work recently about medians, quantiles, and as we've looked at general purpose methods for TP confidence intervals. I think what we're focusing on this work is really the non-parametric aspect. So we want to avoid making assumptions, parametric assumptions, but also we want to avoid assuming that the quantity we'd like to estimate is like normally distributed, which is a common assumption in these works. Okay, so looking at the CDF estimator, again, there's been a lot of different work on privately estimating the CDF. The specific one that we tested out is this one by James Honecker, which is a CDF through a differentially private binary tree. So this is very similar to, I think, in spirit to how the census is computing its noisy measurements. And in this paper, this involves discretizing this range and then combining multiple hierarchical noisy estimates to get measurements for each point in the range. So in this figure, this yellow line is the real data, which is log normally distributed. And then the red points are the DP estimates with the blue error bars. And the aqua line is the population median. So this is the non-private confidence interval in green, which we get by computing these percentiles QL and QU, and then returning the points at which they intersect the real data. So we're returning the values that correspond to these percentiles. And then this is just showing sort of a naive approach to providing private confidence intervals using this union bound approach. And so as you can see, this is in red, and this confidence interval is much larger. And how we get this is looking at sort of the last measurement, which is under the QL, and then similarly above QU to get our confidence interval. But we can do better than this by sort of accounting for both sources of error together. And this is kind of using a hypothesis testing formulation. So if we let F be the true CDF, F hat be the empirical CDF, and F tilde be the noisy CDF, then for every Y in this discretized range, we can compute an AYU such that if Y is less than or equal to the median of X, then the noisy CDF exceeding this critical value is going to be bounded in probability. And using that, we can get a hypothesis test. So we will test whether this noisy CDF is greater than this value. And for our upper limit of our private confidence interval, we'll return the largest value of Y such that the test fails to reject. And we can see that this is valid because the test will fail to reject the true median of the population with the correct probability. And the reason we're able to compute this AYU, which is critical to defining this hypothesis testing approach, is because we know the marginal distributions for each of the noisy measurements. So we know that f tilde y, which is the noisy CDF, is the empirical CDF plus some noise, and this noise is like a linear combination of all the different hierarchical measurements that are taken. So even though all the measurements are correlated, we know the marginal distribution for each of these measurements. And then we can relate, again, the empirical CDF to binomial, and then that allows us to solve for the smallest AYU such that we have the correct hypothesis test and the correct critical value. So going back to this figure, if we now use this approach, we're plotting the AYs here. Sorry, this should be AYU. And then our private confidence interval with this new approach is looking at the last point that is below AY and then the first point that is above AY. And as you can see, this does much better than the union bounding approach for getting tighter confidence intervals. So as I kind of alluded to before, the reason we can do this approach is because we understand the marginal distribution of every noisy measurement. If we, for example, it's tempting to take this noisy CDF with these error bars that is not monotonic and turn it into something that looks like a real CDF using sort of a monotonic projection. But once we do this, it's unclear how to, so if we post-process sort of prematurely in this way, it's unclear how to do this same sort of theoretical analysis. We can still get useful confidence intervals, and there is sort of ongoing work to do this by Marcel and Adam through bootstrapping. But this requires some modeling assumptions that may not be valid. So ideally, if we can get the noisy measurements, we're able to do this theoretically valid approach. Okay, I'll briefly talk about the second method, which is direct computation via the exponential mechanism. So this other approach, so rather than releasing the whole CDF and then post-processing, we're directly tailoring this to the task at hand, which is confidence intervals for the median. So we're using this variant of the exponential mechanism to directly estimate the quantiles we want. And the score function we use for the exponential mechanism is the difference in the rank of the point that's outputted compared to the target quantile. So the question is, which sort of points do we want to estimate? As I said, we can't just estimate the same quantiles that we would like to get for the non-private interval, because this would result in intervals that are too small. So we want to look at sort of expanded quantiles to estimate. And just sort of visually to represent this, so if the green is the non-private interval, we want to choose endpoints to estimate in purple such that the distribution of the exponential mechanism only crosses over the non-private interval with small probability. So now I'll move on to some empirical results. This first plot is showing the width of the confidence intervals as we vary n. So these are box plots showing sort of the distribution of widths over many trials. And we're testing exponential mechanism, the CDF algorithms, and then the non-private log normal and non-parametric algorithms. And the union is this union bounding approach versus the more tailored approach. What we're plotting is the relative width of the confidence intervals. So the width of whatever we're looking at divided by the width of the non-private, non-parametric confidence intervals, which is sort of our baseline. So what we can see is that the exponential mechanism in, so I guess the better one to look at is the maroon, tends to do slightly better than the CDF in pink. but they're pretty similar. So even though with the CDF we're able to release a lot more information, we're still able to get very useful confidence intervals. And we also see that from the union bounding approach to the improved analysis, we're getting much tighter confidence intervals if we look at the pink versus the maroon and the orange versus the light pink. We can also look at the coverage of the intervals. So this is the empirical coverage computed over many trials as we vary the nominal coverage of the interval. So here 1 minus alpha is the nominal coverage in this gray line. So we can see that all of the private algorithms sort of significantly overcover. And one question is this necessary and can we do better? But we see that even though they overcover, this overcoverage doesn't necessarily translate to much larger widths of the confidence intervals. We also see that, again, with the improved analysis compared to the union bounding approach, we're able to get closer to the nominal coverage. So I'll just conclude with some thoughts about what this means for noisy measurements and for our discussions today. So what we've seen is that we can post-process this tree-based CDF estimate into a non-parametric valid confidence interval for the median. And the CDF approach is slightly worse than the direct approach, but still offers quite good utility while giving a lot more information. But if we post-process the CDF prematurely to make it monotonic or to enforce other constraints, then we lose this essential information, which is knowing the marginal distribution of the noisy measurement at each point. And that's what allows us to give these theoretically valid confidence intervals. So I think it's even more important to be able to release the noisy measurements. And with that, I'll conclude. Happy to talk more, take any questions. Thanks.
Interesting talk. Do we have any questions for her?
This is lovely work. Have you been able to apply any of the ideas to other kinds of estimation problems? It seems that some of the notions should be quite general.
So that's a really good question. So, well, one thing is that we were hoping to directly apply the median approach into other estimators that use medians as a subcomponent. But we haven't really looked, at least I haven't looked, I don't know if others have looked at doing this sort of analysis for other problems. What we find is that it does really require opening the black box of the algorithm and requires a lot of effort to understand how these two sources of error interact with regard to the particular algorithm. So it would be nice to have a more general approach.
If you could pull out some techniques specifically that you used for disentangling the two sources of error, I would hope that this would be very, very relevant to the goals of this workshop. So that would be great.
Definitely.
Oh, yeah.
Yeah, really great talk. I really enjoyed it. I'm actually really interested in the CDF estimator. I was kind of curious, are there like tuning parameters or choices we have to make, such as the window or like bin width or things like that? And how did you deal with those choices?
That's a great question. So yeah, so I think the two main parameters are exactly what you said, the range on which we're estimating, as well as the granularity of the like grid point that we're enforcing on this range. And so actually another algorithm that we tested is a combination of binary search to find the correct range and then applying the CDF within this range, because you can sort of waste a lot of your privacy budget if you don't know where the data lies in this range that you're looking at. And that seems to also perform quite well when you have less information.
And what about the like granularity or bin width?
So for us, the granularity, we were constrained sort of by the computational aspect of that. So it can quickly get computationally, I don't know if it's inefficient, but it takes a lot longer. I guess your privacy budget is also split amongst the different, how many levels you are estimating in this tree-based system. So that depends on the granularity as well.
I guess I'm just maybe kind of wondering if did you use some sort of heuristic or a rule of thumb, or like how did you come up with the choice that you ended up using for the granularity?
Yeah.
Oh.
Yeah, for these types of data sets, I forget exactly how finally the the interval was cut up, but it didn't affect much. Basically, once you've got once the window is like not much wider than the data, then you'll get a pretty good median by sort of almost any reasonable kind of choice of the granularity. We didn't like systematically investigate it. It just kind of, we picked some setting that made sense for the kinds of experiments we were doing and just ran with it. I guess in general, it's a good question, but we don't really have a fantastic answer to.
Kind of on a similar note, can you also compensate for correlations between the errors in these different bins, or is there an assumption that they're independent?
No, so all of the measurements are correlated.
Oh, cool.
Because of the tree-based approach. But as long as we know the marginal distributions were
Okay.
good.
Yeah, I heard the hierarchical word in the presentation. Thanks. That makes sense now.
Yeah.
Thanks.